just for any, this you can view at this time, position is C, right? So at SC together, isn't that a point? That's a point, right? On the vector, from the B, from the set B.
At a fixed time.
Yeah, but if S is fixed.
At
Sure.
time S.
Yes. So right now SC, whenever you see this, it's just the first one is time, the other one is position, right?
Right.
Yeah. So this is when this is fixed. That's a point
Right.
from this set B. Yeah. Okay. So of course in that notation we use the SX instead of SC, right? Same. Doesn't matter. So it's still SX. That's just the point, right? Of B from the set. So immediately you recognize for this point you can construct an integral curve. Integral curve will pass x at this time, right? Yeah, that's the initial value problem. So given the initial, this is the initial value actually. So you can construct the integral curve satisfying initial value. And then this curve, of course, is time dependent, right? Yeah, so that's the notation. So you see this is a flow which is depending on TSX, right? Because we define all those components. So it's depending on TSX.
So the integral curve that you can construct based on that IVP is itself time dependent.
Based on the, yes.
And the time is in the interval, right? And
right.
And if it's a complete vector field, so it is any real numbers.
Yeah, because for any point, there is an interval, right?
Right.
Because you will have a solution passing this point. The solution has to be on some interval, right? We know there's a maximum interval where a solution exists. So this is the maximum interval. Yeah, so we have, just to indicate this, this is how we define this flow. That's the definition of flow. Okay, so this definition, but certainly, here's one way to write the flow, right? We can, for convenience, we can also write a flow in this way. V, put S here, T, X. So probably you're not used to this notation, but later you will see convenience of using it.
So P of X.
Yeah, still the three, you see, three parameters, right?
So
no matter where you put them.
Yeah, why do we write ST like that? Is it like an integral?
No, it has nothing to do with the integral. It's just where we put it. We put it as a superscript, subscript, x, but still this is a flow depending on STX, right? Doesn't matter how you put it. So this is a flow in terms of TSX, right? Yeah, so this is one notation for the flow. That is the alternative notation for the flow. Yes, basically the flow, you see, can be depending on STX. Yeah. So just remember they're the same, right? They're just this. That's according to our definition. Okay, so this flow has a special property you can easily verify. Yeah, by the way, at T, if you use this notation, let's write this notation. Right? X, this is X. What does that mean? STX. That's just an integral curve, right? At another time, at T, right? You see, this is, even if you're not familiar with this notation, but let's refer to this one. That's the integral curve at the T, at time T. So that's the value, right? That's the solution. That's the value of the solution.
Isn't that the flow?
That's the time. At this time, that's the value of the solution.
Oh, it's the flow, but at that time, it's the solution, right?
Yeah, this is the alpha value. This is the alpha value at this time, right? Yeah. So what do you think? This must be a point B, right? A point in B. Right. Because Yeah, in order for the vector field to be defined, if it's a solution, it has to satisfy these equations, right? So at that time, that's a curve. So that t, right, you put here, that flow in that notation, which is just alpha, right? Alpha at t. So it's really this part. Of course, if it's a solution at time t, it should satisfy the vector field. So this has to be a point in the domain of the vector field. So this has to be in B. Yeah. So we know that's just a point in B. And also here's another property. What if I put S? If T is the same as S, what do we get? Yeah. Okay, if you're not familiar with this notation, let's put if T is same as S. Or here, maybe. That's the integral curve when time is S. What do we have?
X.
Yeah, X, yeah. In this notation we use
X
X,
of
right?
X equals
It's
C,
X.
so it'll be S, right?
Yes,
X.
so it's X. Correct, because we know this is an integral curve passing through this point. So when time is S, then the curve will have a value X. Yeah, so that means this is this one is an identity function, right? Identity function for whatever input. That is identity on what? On Rn. Because X is a point in dimensional in Rn, right? So for whatever X, this one acting on X is still X. So that's an identity function on Rn. Yeah, so if this is also belongs to the domain. Yeah, to make the vector field defined. Okay, so now one property. This property. The domain of the flow is an open set. Okay, so that flow we just defined. This flow has domain d tilde. This domain, the set, is an open set. Yeah, we're going to use this property later. So, but we just listed the property here without proof. So, yeah, because it's open, here we have this. We can write, if it's an open, that means we can find an open set from Rn, right? So it's possible to find U, that's a that we will find an open set U, which is a subset of Rn. We can also find an open interval, right? I, which is a subset of R. Yeah, then this, yeah, we can pick any point. So let's just fix one point. Suppose this is a point from the B. Because now we're looking at D, so right now this is a set with these components. So d tilde, we just pick 1 point from d tilde. This point, it is at some point t0 if the solution passing through this point, right? So this is just 1 point from B. This is 1 point from B. And we, because of the definition of d tilde, we think we use another time. This time we just pick a very special time, which is same as this second, the S, right? So make them the same. Because this is open, that means you can find an open set including C. So we can find an open set U with C as an element of U, right? In this. And also you can find an open interval with T0 as an element of this interval, which is R. So then we can actually construct this set. So this is a subset of Rn, which is open. This is an interval, including T0. Yeah. So we just consider this, which is just a subset of d tilde. Okay, so on this subset, we look at the map again. So we just suppose you view this as a 2-parameter family. So this one, we actually want to fix S or T or both. So let's see, for this one, X is from this U, right? Because S from this interval, T from this. So X for any X from this open set U. What's the image? This flow map. If we view this and view X as input, if we fix S or T, although that was a 3-parameter, right? Flow depending on 3 parameters. But let's just fix those two. Then for any X from this open set, it maps to where? What kind of object is? Don't forget the definition. Yeah, the image will be just the curve alpha, right? That's the value of this. So the value of alpha.
So yeah, it'll be in Rn.
Yes. Yeah, in Rn, or maybe in a subset of Rn.
Oh.
Yeah, we can use this notation, which is some subset of Rn. Yeah, it all maps in Rn.
Aren't the times the same?
Aren't
the times the same? Like T naught, T naught?
Yeah, so this is just some open set, including this point. Because the flow is continuous, right? Yeah, the flow is a continuous curve. This curve, so if we're not far from this point, so it's possible to find interval for both S and T are in the same interval. Yeah, so we just restrict ourselves to such an interval so that we just pick ST from I, right? Whenever ST are from the same interval, then we know this is defined. Just we view this as some flow depending on X only. We can fix the 2 other parameters. Then it's from the open set U to this. So it's like a position.